So welcome everyone to this Big Things meetup. Today we are very glad to host Jon Bratseth, who is a VP architect of the Big Data and AI group at Verizon Media. And not only that, he's also the architect and one of the main contributors of Vespa.ai, which is an open source big data serving engine. As Demi mentioned, just for a few guidelines. So if you have questions, you can either wait until after the presentation and unmute yourself and ask them, or you can ask them during the presentation using the chat, and we'll read them out loud at the end of Jon's presentations. Other than that, enjoy having fun, and Jon, to you.
Thank you. Let me share my screen. Can you see this? All right. So I'm talking about big data serving, which is about processing and doing inference at scale in real time. So I'd like to introduce this by talking about maturity levels that organizations go through as they start making use of the data. First, they are in what we call the latent stage, which is when they produce data, but they don't really use it for anything systematically. So if they use an example of a proto Netflix, they will do movie streaming and log whenever somebody streams a movie, but they're not really using it for anything. At some point, they get the idea that they want to start using the data to improve the service or product or whatever they are doing. At that point, they enter the analysis phase, where they start using various tools to pull out information from the data and present that to humans, such that the humans can make better decisions. That's the typical analytics tools like data warehouses, log analysis tools, and so on. Right. So in the movie streaming example, that would be automatically creating lists of popular movies for various audiences and show that to editors so that they can curate lists that are presented as the recommendations to users. At some point, you want to take the users out of the loop here completely and automatically learn what you present to users, or in more in general, learn the decisions that you want to make directly from the data. And that's when you get into machine learning. So in the movie example, that would be automatically learning the right recommendations per user segment directly from the data, right? So that you don't need human editors to do that job by looking at what you extract from the data. So that's pretty good, and most organizations aren't really there at all yet. But there's another phase as well, which we call the acting phase, which is where you make decisions directly from the data in real time. So that is online when you need the decision. So the example, the movie streaming example here would be when a user opens the application or wants to look at a movie in Norway, you automatically at that point compute a list of recommendations for that user from the data you have about what movies and so on users are looking at, right? And that's what we call big data serving when you get to that stage. So it's selection, organization, and typically machine learned model inference over lots of data that keeps changing all the time, and where you're doing it online so that you need low latency and be able to handle high load. So in short, it's AI plus big data plus online. So why do you want to use big data at all? Well, in some use cases, it's absolutely necessary. The canonical example is big search systems such as web search. It's big data because you actually want to search all that data, right? So that's baked into the use case. And recommendation is similar because you have lots of stuff you want to recommend. That's part of the reason you want to do recommendation at all. So you actually need to compute over all that data, right? And there are other use cases like that as well. But in other use cases, you don't really have to look at all that much data, but still looking at more data typically improves decision making. And you can view that as two different ways of doing AI, right? If you do what you might call intuition AI, you compress all the data that you have into some simple function. And that's really what you're doing with machine learning, right? But there's another kind of AI, which is deliberate reasoning, where you look at concrete data to deliberately make decisions based on that data, right? And just like humans, computers needs both kinds of AI. And that means having access to big data in these other systems where it's not that obvious that you actually need it as well. And we look at an example later, which is question answering, where we actually do both the intuition AI kind of thing and deliberate reasoning as well. So that's why you want to use big data. Why do you want to make decisions online? Well, there are several advantages to that. One is that decisions are using up-to-date information. And that's two aspects of that. One is that you use up-to-date information about the world. For example, in the movie example, you have all the latest movies and TV series and whatnot available when you make the decision, even if they were just released, right? And the other aspect is you use up-to-date information about the user or context or whatever about the decision, right? For example, if a user was recently looking at something and so on, you can incorporate that into your next decision, which you can't typically do if you do it offline because you don't have that information available, right? Since you're computing on demand, at the moment you need to make a decision, there's no wasted computation. Only those decisions that you actually need will be made, while if you're pre-computing everything from the data, then you need to compute for every possible scenario that you will encounter while online, right? And for that reason, when you're making decisions online, in real time, you can make very fine-grained decisions. You can incorporate all the information that you have about that particular case. While if you're doing it upfront, you need to limit the number of things you compute, and therefore your decisions need to be more coarse-grained. Otherwise, there will be too many of them. For example, from the movie site running example we have, you can't compute offline typically a separate recommendation list for every single user because it's just too expensive. So what you do instead is you bucket the users in prototypical buckets and then you compute for those. And obviously that's not as good. And once you have a component that can do this big data thing and compute online or lots of data, then the rest of your architecture becomes much simpler. So what we see even in very advanced companies that don't really have these capabilities, that they create a very complex architecture to compensate for the problems above. They need systems to take their offline computed decisions and send them to data centers around the world where they will be served. And because the decisions are not really using up-to-date information, they typically develop auxiliary systems that compensate for that and so on. So the whole thing becomes very complicated. While if you have a component that can do this, you just give it all the data and you send it queries and that's it. So it's very simple. So that's why we believe that big data serving will be the way everybody's doing applied, the applied part of applied AI eventually. But when we'll get there depends on the use case, obviously. So why aren't everybody doing this already? Well, it's because it's very hard, right? You need to handle mutable state, and lots of it, and do distributed computations over this state with stable low latency and high availability. And all those four problems are difficult on their own, but here we need to solve all four at the same time. So in more detail, you need to make real-time actions, typically do everything you need to do for a single decision or query in tens of milliseconds, because humans don't really like to wait for anything more than about 400 milliseconds. and you need time for transferring to and from the user and so on. So that typically translates to a latency budget of less than 100 milliseconds. Because you want to handle real-time knowledge, you need to typically deal with high update rates and continuous update rates. So the data keeps being updated all the time while you're handling queries. You need to handle that. And you need to scale both to big data volumes, but also to large query rates, because when you're dealing with stuff online, there's lots of things going on, lots of humans interacting with your system and so on. So you need to compute for all of those things that happen, right? And because you need high availability, you need to be able to recover from hardware failures without any human intervention at all. And you also need to be able to change everything while you're serving, change the data schemas, change the business logic, the machine learning models, even the hardware you're running on while you're serving. And you need to integrate with the rest of the big data stack to get data from your data lake, typically the systems that actually do the machine learning and so on. So that's obviously way too much work for most organizations to solve on their own. And for a long time, nobody could do it at all. But then we got one particular use case, which was profitable enough that it could fund all this development. And that was web search. And Vespa was developed as part of the web search effort inside Yahoo. Actually, we were a separate company before that and were acquired by them. So in that group, we developed two technologies, one for handling the offline part, which was Hadoop, and one for handling the online part, which was Vespa. And the core idea of both is the same, which is to move as much computation as possible to the data rather than moving data to some computation node as you do in a typical 2 or 3 tier system where you have traditional databases, right? We could open source Hadoop right away, but we weren't able to open source Vespa because of the complex IP rights around search technology. But finally, in 2017, we were able to open source it. So now this kind of technology is available to everybody as open source. So just some example usage from the company I know best, which is now Verizon Media. So we have a cloud service that we serve these use cases for. So I know a lot about it. We have a few hundred Vespa applications that we serve for them, serving over 1 billion users, about 450,000 queries per second in total, and a few 100 billion content items. And some of these applications are things like computing all of the articles and videos and so on that will be shown in all the apps and pages like Yahoo Finance and News and so on when a user visits that page or the app, because all of that content is personalized, right? And personalization is just the same as recommendation. So it's computed in real time whenever a user shows up, using as input what we know about that user. And we do a similar thing in another Vespa application to compute what's called native ads, which are ads that are typically inserted in streams like this, like the thing about Norway in this picture, where we also do run a real-time auction and so on to figure out the final ad or ads that will show up for the user. So that's just some examples. Then we'll look at some a couple of use cases in more detail. And as I mentioned, the canonical use case for big data serving is obviously search. In this use case, the data items are text documents and your queries are actually keywords, actual keywords that the user types. And you have a machine learning model that computes relevance between the text document and the keywords using metadata and so on in addition. And you select items by that machine learned relevance function. So Vespa can do the full stack traditional search, which is full text indices with positional information, support for fast evaluation of GBDT models, which is the machine learned models that are traditionally preferred in search applications. We provide a lot of text match relevance features, snippeting, linguistics, text processing, and so on. All the stuff that you need to create traditional search applications. Over the last 2 to 3 years, there's also been a movement towards what some people call Search 2.0, where you get rid of all of this complex stuff about linguistics and full text indices and so on, and instead use a machine learned model, typically a transformer model, to convert the text to tensors, typically some dense vector representation, but not always. And then you use vector similarity search to find relevant documents, and then you do a final more complex evaluate a more complex neural net to compute the final relevance for the best matches according to your vector similarity search. And Vespa can do that as well. It has a native tensor data model and computational engine that allows us to express these kind of machine learned models that I mentioned. And we also have support for approximate nearest neighbor vector search. And you can evaluate complex machine learning models like transformer models and so on inside Vespa on the data nodes themselves, which means it scales with your data volume, right? But the nice thing about Vespa is that you can also use both kinds of technologies and draw from both kinds of information in the same query and combine both kinds of information in the same relevant score, which typically yields superior performance to either approach on its own. The other use case that is far along, and at least on Vespa even bigger than search these days, is recommendation / personalization / targeting. Here the data items are anything that can be recommended. I've seen Vespa applications that do anything from images, videos, news articles, clans you should join in computer games, people you should match up with in dating apps. There's lots of stuff that can be recommended to people, right? It's really about selecting something for somebody out of a wide range of possibilities. So it's a really wide use case, maybe even more so than search. In this case, the query is typically some model of the user and or the context that the user is in, as well as some filters that filters out undesirable content. For example, in ad targeting, that can be ads that have spent their budget. If you're recommending news articles, it can be articles that are in the wrong language, all kind of things like that. And the machine learning models that you evaluate are typically some recommender model or models that you combine. And then you select those that have the highest score according to that model again. And all that you can do natively in Vespa as well. It has a tensor data model and computational engine, as I mentioned. You can put in models learned in TensorFlow, ONNX compatible tools, XGBoost, and so on directly into Vespa. And you can do either fully accurate vector search if your data volume isn't that large, or if it's really large, you can use approximate nearest neighbor search. And when you do that, you can combine it with filters and still have efficient search, which is something you can't really do when the approximate nearest neighbor search implementation is separate from the rest of the index. Another use case, which is much less far along, but still quite interesting, is using big data serving for finance. Here your data items are typically assets, like for example stocks, and your queries are some kind of updates to the world state, and you have a machine learning model which is a price predictor. And here you select items typically by the largest change according to that model. And if you do this, then your result will be that you find the assets that change most in response to an event using completely up-to-date information about the world. And you can do it faster than anybody else, which is obviously quite useful to some people. Last use case I mentioned because it ties into what I mentioned about using big data, concrete information, also in a use case where it's not obvious that you're doing search or recommendation or something like that, which is question answering. If you're not familiar with question answering, the point of it is to simply to answer questions. As you can see an example over here, the question on the top here is, when was the last time anybody was at the moon? And the answer is December 1972 or 14 December 1972. And the way this is typically implemented is you take lots of text passages, in this case from Wikipedia, and you index those, but you do index them with the search 2.0 approach where you encode them as a vector. And then you encode the query in the same vector space, and then you use approximate nearest neighbor search to quickly retrieve candidate snippets that are about your question. And once you have those candidates, you evaluate a much more complex machine learned language model, typically a transformer model like BERT or something like that, on both the query and each of the candidate passages. And these models are able to spit out a score for each candidate answer, as well as the positions of the token start and stop for the actual answer itself. So the end result is that you are able to actually come up with a concrete answer to the question, not just a candidate phrase, right? And all of that can be implemented as a single application on Vespa. And we have some blog posts here that explains how we did that and how we got end-to-end latency below 100 milliseconds while having state-of-the-art accuracy like you will get from the latest research papers on this topic. Okay, so that was some example use cases. One question I often get is about how big data serving is different from analytics. So this slide is just about that. With analytics, which is what you want to do when you're on the stage 2 in my maturity levels that I showed earlier, they're the ones that are looking at your data are your employees, and the requirements are therefore quite different. Response times can be in low seconds, while with big data serving, they have to be in low milliseconds. And you have low query rates, while in big data serving, you have high query rates. And typically with analytics, you only look at time series data, while with big data serving, you want to keep your data up to date, augment it, and so on. So you typically have random writes. And since you're dealing with employees, also you can have downtime, lose data, and so on. While with big data serving, none of that is acceptable. So all those things are harder with big data serving. And the flip side of that is that with analytics, you can typically find ways to index massive data sets, trillions of documents cheaply, while with big data serving, it starts to get really expensive once you get past a couple of tens or hundreds or billions of documents. Okay, so we covered what big data serving is, and we talked a bit about Vespa, the big data serving engine, and some use cases. And now we'll look more into the architecture of Vespa and how it solves the big data serving requirements that I mentioned. Handling state, high availability, low latency, and so on. So Vespa is a platform for low latency computations or large evolving data sets. So it can do full text search as well as selection over structured data and search in vectors as well. and it does scoring / relevance / inference over the selected data. It can compute natural language features for you and or advanced machine learning models imported from TensorFlow, MX, and so on. I haven't mentioned it, but it can also do query time organization and aggregation over all the matching data. So that's a kind of distributed algorithm you can run over the data as well, including running data sketches to count stuff efficiently and so on, which you often want to do to extract statistics about the data or show word clouds or graphs or navigational tools or collapse things that are too similar and all the kind of things like that. It can run queries doing all of this while it's handling real-time writes as a high sustained rate. Typically, each of the nodes can handle a couple of tens of thousands of writes per second sustained. And the important thing here is sustained. It's easy to do this in short bursts, but if you want to keep doing it with predictable latency all the time, it's just much harder, but also much more useful. And the clusters that are doing this are live, elastic, and auto-recovering, so you can add and remove nodes as you go, and the data will just rebalance in the background while you're handling the writes and the queries. We also have a processing logic container on top, where you can add your Java business logic. And because these systems can be complex and consist of up to a couple of hundred of nodes with lots of processors and so on, you don't want to configure the whole thing yourself. So Vespa provides managed clusters where Vespa sets up everything for you, and what you're seeing is a much more high-level description of the system that you want to run. So high-level architecture looks like this. So Vespa is a two-tier system where the incoming queries and writes and document operations and so on enters the stateless Java container cluster or one of the clusters that you want to have in your application. This will execute the global part of the algorithms that you need to run to execute the query and so on, but you can also plug in your own business logic to handle queries or implement your own APIs or change results or whatever. Below that, we have what we call content clusters that stores the actual content and evaluates the distributed part of queries, as well as handling redistribution of data when there is a change and things like that. And lastly, because these clusters can be large, they are managed. So there's an administration and configuration cluster as well that sets up this for you. And what you see as a user is what we call an application package, which is a high-level description of the application that you want to run. What kind of clusters do you want to have? What components do you want to run, if any? What's your machine learning models, if any, data schemas and so on. All that goes into the application package. You never really configure the nodes themselves. You just deploy the application package to the admin system, which will then set up the final system for you. And when you want to change your application, you just change the application package and deploy it again. And the administration and config system will figure out the delta between what you're currently running and what you want to run and safely move you from one to the other without any disruption to the query traffic and writes. So the whole point of this really is to be able to do low latency computation. And there's three main strategies we use to do that. First, we parallelize. So when you get a query, it's scattered to all the content nodes that have relevant content in parallel, so that they evaluate on parts of the content in parallel. And on each of these nodes, the query is again sharded to dynamically to multiple cores that will evaluate over part of the data and communicate between each other to bring down the latency even further. Secondly, we prepare data structures at right time and in the background. The typical example there from text search is posting lists. We also do B trees for the structured data, as well as HNSW indices for approximate nearest neighbor search in vector spaces. So an example, and lastly, we move as much execution as possible to the data nodes, right? So rather than pulling the data up to the container node, we do most of the processing down on the content nodes, and that has two effects, right? One is that we can parallelize because they compute over subset of the data in parallel, but also we don't run out of bandwidth between the content nodes and the container nodes, which you surprisingly quickly do otherwise. And that's not just local bandwidth between these nodes, but it's bandwidth in your data center, right? So it's very hard to scale once you hit that limit. So an example of that is if your application package has machine learned models, when you deploy, those are copied to the content node so that they can be evaluated locally over the local data, right? So this is just a graph from an experiment we ran where we compared evaluating a machine learned model in TensorFlow serving, which is stateless, to doing it in Vespa. And you see you get comparable performance if you only have one data partition, but once you add more data partitions, that is content nodes, then you get almost linear scaling in Vespa, while in TensorFlow you get no benefit from this because you really run out of bandwidth in your data center. So a bit more detail about what content nodes really do for those that are interested. We do what's called document at a time evaluation over all the operators or query in parallel. And that's because we want to be able to evaluate nonlinear machine learned models over all of the matching documents. So we need to have all the information from one document in memory at a single point in time, right? We do for index string fields, which is the traditional text search posting list fields. We do positional text indices, dictionaries, posting lists for not recently changed data, and then we do B trees in memory for recent changes. And then we combine both kinds of information when evaluating a query, and that's how we are able to update the positional text indices seemingly in real time, because that's very expensive to do. So what we do instead is we write recent changes to B trees in memory, and then we flush those B trees and merge on disk in the background to sustain the write rate. We also have what we call attribute fields, which are columnar storage of structured data, which you can access in your machine learned evaluation during grouping and aggregation, but also for searching and sorting and so on. Those can optionally have B trees built over them as well if you use them as strong criteria, strong filters in your queries. And lastly, we do indices over vector fields, which are based on the HNSW index type, which allows us to do efficient approximate search over vectors. And then since most of these changes, all these changes are real time, and that means they are at write time when you change or add or remove a document. All the changes happen only in memory so that we can apply it very quickly, right? But we also want to guarantee that changes are persistent, right? So we do the similar strategy that databases use, which is to use a transaction log for persistence that allows us to replay recent changes if we suddenly go down. And in addition to all of that, we have a separate store of the raw data of the documents themselves that we use for serving actual data content, as well as doing recovery and redistribution when you change your cluster nodes or suddenly some nodes go down and you need to redistribute data. And you can have multiple schemas as part of your application, and then you have one instance of all of the above for each of the schemas. Data distribution in Vespa, for those that are similar or familiar with how this is done in Elasticsearch and so on, it's not like that in Vespa. Vespa auto distributes data over a set of nodes. The only thing you specify really is the set of nodes and the replication factor you want for the data. You can also add some additional control to have data in multiple groups and so on to scale to even higher query rate. And then Vespa takes care of the rest of its own. There's no manual partitioning or placement of partitions or anything like that. It's all algorithmically based. And if you change the number of nodes or change the configuration that you want, like adding or removing groups or whatever, Vespa will just redistribute the data in the background automatically for you. A bit more detail on the approximate nearest neighbor search is a big thing that we released this year. It allows you to search billions of vectors per nodes, where each of the vectors have a few thousand numbers and still return results in milliseconds. So that's a very big leap from what you could do before, where you would struggle to do that above a few millions. And the unique thing about the approximate nearest neighbor search in Vespa is that it's still efficient if you combine it with full text search and or filters, which is something you can't really achieve if you're doing your filter and or full text search first and then doing your approximate nearest neighbor search, or if you do it the other way around. Both are just wrong. You have to do it interleaved or as you move through the document space, and that's what Vespa is doing. And the vectors can be updated in real time with a few thousands of writes per second sustained. And we achieve this by having our own modified HNSW implementation in C++ inside the Vespa core. A bit more detail about inference in Vespa. We have, as I mentioned, a tensor data model. A tensor is just a generalization of vectors, matrices, and so on, where you can have any number of dimensions, right? So it's really a multi-dimensional collection of numbers. And you can add those to queries, and you can make a document field from them, and you can put them in your application package as part of machine learning models or whatever. And then you have a tensor mathematical language that allows you to compute over these tensors using mathematical operations like join and map and reduce and so on. And you can write those mathematical expressions by hand if you want precise control over what you're computing. But what lots of people want to do instead is to just learn a model in TensorFlow or Scikit or something like that, and then export it and just put it in your application package and let Vespa run it for them. And you can do that because we have compatibility with those tools. Tensor dimensions in Vespa.ai can be both dense, which is the familiar form that everybody supports, but they can also be sparse, which is more like having a mapped dimension, right? And you can have mixed tensors that have dimensions of both things, which allows you to do things like maps of vectors and all of the kind of things like that. And you can still do mathematical operators over tensors with both kinds of dimensions, and they work the same. So we have a small set of these join, map, and so on functions that forms a universal language that we have implemented our runtime system on top of, but we also provide a large set of the higher level functions that you can see examples of here from the documentation that really maps to those primitive functions, just to make it simpler to work with for computer scientist kind of people. So here's just an example to build the intuition for how this works for things like a TensorFlow model. This is a graph of a very simple TensorFlow model on the left, and Vespa can automatically translate that for you as part of the deployment process into the equivalent mathematical expression in the Vespa language, as you can see on the right here. So what we have been working on quite a bit recently is to support much more complex models here. And we can now support complex transformer models like BERT models and so on, and still provide, in some cases, very good performance depending on the complexity of these models. Sometimes we translate to this internal language, and sometimes it's faster to just use ONX runtime. So we have integrated ONX runtime inside the Vespa core as well. Okay, so a little bit at the end about how we do releases in Vespa. So Vespa is developed in the open at github.com. We don't have our own internal copy in my team or something like that. We just develop everything out there so other people can participate as they like. And it used to be, we did this and everybody else did this. We released a new version of Vespa about every year or something like that, a new major version with lots of new features. And then we branched off and did bug fixes and so on all branches. A couple of years ago, we moved to a continuous deployment model instead. So we don't do that anymore. Instead, we create a new production release Monday to Thursday every week. And all new features are rolled out incrementally as part of this production releases. And the only times we change the major version is when we break compatibility because we want to garbage collect lots of old stuff. So that's about every second year or something like that. When we publish or release, it has passed all our functional tests as well as performance tests that ensures that the performance is at least as good as it was before. But we have also already deployed it to the about 150 production applications that we run as part of our cloud service. So they are already run about 450,000 QPS per second for a couple of hours when we push it live or publish it, I mean. And all releases are backwards compatible unless it's a major version change every second year, as I mentioned, which means you can do upgrades live node by node, which is what we do or on the cloud service that we provide. Okay, that's all the material I had. To recap, if you want to make the best use of big data, it increasingly means making decisions online, computing in real time when you need the decision made. And Vespa is the only platform that is written to solve those use cases. It's available at Vespa.ai. You can find some quick starts there that allows you to clone and deploy your own app, and you can run it on our cloud service for free if you like. There's also tutorials there that takes you through the process of building a blog search and recommendation engine from scratch. We have the question answering application up there and a couple of other examples as well that you can look at, both the code and how you actually train the models and so on, that you can follow if you like. So that's really all I had. Are there any questions?
Yeah, so I'll start. How difficult is it to deploy Vespa cluster based on the open source offering by yourself? I mean, given all the moving parts that there is with the system components, what would it take for someone to just experiment with a local installation of Vespa?
Yeah, well, if you want to experiment and you don't want to use the cloud, which is the very simplest thing you can do, you can just run it on your own Mac or PC using Docker as a single node installation that runs everything. And there's a quick start guide that tells you step by step how to do that. So that's not hard. If you want to set up for production, it's little bit harder, but not that much. There's a step-by-step guide for that as well. It basically amounts to having a bunch of Docker nodes or Linux nodes with RPMs and just install Vespa on them and just set one environment variable that points to the configuration cluster. And then you just deploy to that and it will run for you. So that's quite simple as well. The thing that is where it gets a bit hard and where it helps to have to use the cloud service instead is continuous operations, doing upgrades while you're having live traffic and handling various operational issues that happens and things like that. That's where these systems are typically very hard and harder than other kinds of systems because you want to operate with low latency all the time while you're doing this gather where all the nodes that have problems and so on can interfere with every query, right? So that's where you really have a value add, I think, from the cloud service and where you need to have people that knows what they are doing to run it themselves in production. Other questions?
Nobody wrote anything on the chat, so I think no. But actually, people asked if we'll be able to share the presentations and not only the recordings.
Yeah.
Okay, great. So we'll add that, attach that to the YouTube link.
Yep.
Great stuff. And somebody else actually asked whatever I asked right now. We'll attach it to the YouTube link and post that also on the Facebook group and on the meetup.
Yep.
Cool. Any other last words by Itai?
Just want to thank Eran for doing the initial intro and for Jon for doing it for the group. I think it's very interesting for our Big Things members to see various big data distributed systems. There are so many out there, but not everyone are willing to share their knowledge and wisdom. So we really appreciate it, Jon. And yeah, thank you everyone for joining.
Thank you very much. Have a great evening.
Meetup. Bye everyone.